Have you ever paused to consider what it truly takes to build software that doesn't just run, but
Yeah.
thrives? Software that's reliable, easy to maintain, and can actually stand the test of time, even as its complexity, grows exponentially.
It's a huge challenge.
Today, we're diving deep into the fascinating world of engineering software, drawing our insights directly from Randall Hyd's comprehensive Write Great Code, Volume 3.
Great book.
Yeah, our mission is to give you a kind of curated shortcut, unpacking the systematic approaches, the various development models, and the crucial documentation practices that elevate coding into a disciplined engineering endeavor. We'll explore how these principles ensure quality, manage complexity, and even define the very roles within a software team, all while still, hopefully, celebrating the individual brilliance of programmers.
Absolutely. That balance is key.
So let's kick things off by thinking about software itself. What truly sets it apart from, say, a physical product like a car or a building?
Well, Robert Pressman's perspective, which the book highlights, is really illuminating on this. He says software is developed or engineered,
Right.
not manufactured like you'd think of a car in an assembly line.
Okay.
The physical cost of producing software, stamping a disk back in the day, or just electronic distribution now, is incredibly low.
Almost zero.
Really, pretty much.
Yeah.
And the design choices themselves, they don't really impact that physical product cost much at all.
That makes sense.
But what's truly counterintuitive here is that unlike hardware components that physically degrade over time,
Yeah, they wear out.
exactly, a defect-free piece of software, once it's correct, will theoretically continue to work indefinitely.
So if that's true, why are we constantly updating, patching, debugging? It feels like it does wear out.
Well, that's the interesting part. The insight is that software degrades not really from use, but from changing environments, new requirements popping up,
Ah.
and discovering those hidden edge cases you didn't know about. So essentially, its relevance and its fitness for purpose wear out, not the actual underlying code itself.
That's a really crucial distinction.
Yeah.
Okay. And speaking of the people who create this unique entity,
Mm.
the book explores various metaphors for programmers. Are they artists,
Yeah.
architects, engineers, craftsmen?
Yeah, all those different hats.
It also mentions the cowboy coder, which sounds like a character from an old Western, just galloping into the code, no map, no plan.
Right, just hacking away.
Fun for maybe a personal project, but
Yeah.
try building an air traffic control system that way.
Oh boy, yeah, you'll quickly be in a heap of trouble.
Right.
And expanding on that, the very field of software engineering is actually defined pretty precisely by the IEE.
The Institute of Electrical and Electronics Engineers.
That's the one. They define it as the application of a systematic, disciplined, quantifiable approach to development, operation, and maintenance of software.
Systematic, disciplined, quantifiable. It sounds very engineer.
It does. It implies a structured approach, much like other engineering fields, often constructing large systems from predefined building blocks.
But then where does the individual skill, the creativity, the artistry fit into such a disciplined framework?
That's the big question, isn't it?
After hearing about those structured definitions, what I found particularly compelling in the book was this idea of the craftsman model.
Ah, yes.
This paradigm emphasizes that people matter. It suggests that training individuals better, allowing them to apply their natural talents, that leads to higher quality software.
Rather than just throwing more people and restrictive rules at a problem.
Exactly. The source really champions this, seeing it as kind of the ideal path for anyone serious about becoming a truly great programmer.
And one of the most, I think, profound observation that the source makes is the distinction between the term software engineer
Okay.
and the actual practice of software engineering.
How so?
The practice, the book argues, largely involves economics and project management. It's often done by managers and project leads.
Right. The planning, the resource allocation.
Precisely. And the people we commonly call software engineers, the coders, they simply write the code specified by the actual software engineer.
Oh, wow. That's quite a statement. It makes you wonder, if these roles are so distinct, why do we use the same title?
It does raise questions, doesn't it?
Yeah.
About what the title really means.
That's a fascinating point. It really highlights a tension in the industry, I think. The title suggests this broader engineering discipline, but often the day-to-day for many software engineers is, focused pretty heavily on coding. It makes me think about how clearer definitions, even just internally, could help teams function maybe more effectively.
Could definitely reduce confusion.
So with that in mind, if software is this unique kind of evolving entity, how do teams actually build it? What are the common roadmaps? And Importantly, how do we even know if we're on track?
Yeah, how do you navigate that complexity?
Let's talk about the different roadmaps teams use, maybe starting with the most unstructured one, the informal model.
Ah, the hacking away model.
Exactly, which, can be fun and independent.
Sure, for small things.
But the book points out it often leads to invalid systems for anything beyond really small throwaway programs.
Yeah, not scalable, not maintainable usually.
So from there, we see an evolution towards more structured sequential models, like the waterfall model
The classic.
and the V model.
Right. The V model is particularly interesting because it really emphasizes implementing test cases and procedures early on.
That sounds like TDD, test-driven development.
Exactly. That's the practice.
Right.
And the idea is you find and correct bugs much sooner, which makes the whole process cheaper and faster in the long run.
Makes sense. Catch them early.
But the downside is these models can demand too much perfection in the early stages.
Like you have to get the requirements absolutely perfect before moving on.
Pretty much.
Yeah.
And they often struggle when requirements change once a phase is supposedly signed off, which, let's be honest, happens all the time.
Oh, constantly. So what came next?
Well, this is where things get really interesting, addressing that rigidity.
Yeah.
You get the iterative model and the spiral model.
Okay.
The iterative model directly tackles that weakness of the sequential models by explicitly building in user feedback through multiple development passes.
So you build a bit, show it, get feedback, adjust.
Exactly. Rinse and repeat.
Nice. And the spiral model.
The spiral model takes it a step further. It's described as heavily risk-based.
Risk-based. How so?
It means you're constantly assessing potential risks in each iteration, each loop of the spiral, and planning based on that.
Okay. Sounds thorough.
It is, but the book also cautions that it's difficult to apply to others because it tends to be very project-specific, and it definitely increases management complexity.
So maybe not for every project.
Probably best suited for really large, risky projects where that level of overhead is justified.
Gotcha. This whole evolution in thinking, it seems to lead naturally towards
Absolutely.
agile, right?
It absolutely does. Agile is described as incremental, iterative, and evolutionary,
Right.
building on those ideas.
And its key characteristics, things like breaking projects into short sprints.
Yep, typically 1 to 4 weeks long, and having those brief daily stand-up meetings.
The 15-minute ones.
Usually, yeah, no more than 15 minutes, ideally. For rapid feedback, quick problem identification. What's blocking you today?
And Agile also deliberately de-emphasizes heavyweight documentation, doesn't it?
It does. The focus shifts more towards working software as the primary measure of progress, rather than comprehensive docs up front.
Okay. And within Agile, there are specific methodologies. The book mentions extreme programming, or XP.
Yes, XP is highlighted as a widely used one. It's guided by values like communication, simplicity, feedback, courage, and respect.
Values driving the process. Interesting.
And one of its more, let's say, controversial practices is pair programming.
Ah, two programmers, one keyboard.
Essentially, yeah. 2 programmers working on the same code together at the same time.
That sounds potentially inefficient, or maybe annoying.
Well, that's the common reaction.
Yeah.
But what's compelling about it, and the source actually backs this up with data, is that while pairs might spend about 15% more time on programs than individuals,
Okay, so is slower?
initially maybe, but the code actually has 15% fewer defects,
Oh, wow. Okay.
and it also tends to lead to better design quality because you have 2 minds constantly reviewing and discussing.
Fewer bugs and better design. That 15% extra time starts to sound like a pretty good trade-off.
It often is, yeah.
But XP, like you said, it's not a silver bullet for every single scenario, right?
Definitely not. The book points out it really shines with smaller teams, ideally around a dozen engineers or so.
Okay.
Beyond that, its kind of all-or-nothing approach can become a major bottleneck if you don't follow every single tenet closely.
Right, you can't just pick and choose bits of XP easily.
Generally, no.
Ah.
And here's a really sharp insight from the source. XP relies heavily on unit tests.
Which is good, right? Ensures things work.
It is good for ensuring existing features work. But it can ironically make teams kind of blind to missing features.
How so?
Because all the tests might pass, showing the known requirements are met perfectly. But the product still isn't quite what the market actually needs or wanted. It can lead to a type of feature creep in reverse, almost.
Huh. Fulfilling the spec, but missing the point. I hadn't thought of it that way.
Yeah, it's subtle. The book also mentions Scrum briefly, another agile methodology known for its iterative framework, but notably leaving the specific engineering methods, like how you code or test, up to the development team itself.
More flexibility there, perhaps?
Potentially, yes.
So, okay, we've picked a development model, we're building stuff. How do we actually measure the greatness or complexity of the software, or even a programmer's output? That seems really hard.
It is notoriously difficult. The book delves into several metrics people have tried. You might hear about executable size or statement count.
Simple counts?
Yeah. But it gets more interesting when it talks about things like cyclomatic complexity.
Cyclomatic. What now?
Cyclomatic complexity. It essentially measures the number of independent paths through your code.
Okay. So more paths means?
A higher number often means more complex code, harder to understand, harder to test thoroughly.
Got it. Makes sense.
And then there's the old classic lines of code, or LOC.
Ah, LOC. Everyone knows that one.
Right. And it's still widely used, mostly because, well, it's incredibly simple to count. You can do it with a basic command line tool.
So ease of measurement trumps accuracy.
It often seems that way. It's almost ironic, isn't it? We build these incredibly complex systems.
Yeah.
But the moment we try to measure the work involved, we often fall back to something as basic as counting lines.
Huh.
The force makes it clear that despite tons of proposed, more sophisticated metrics, very few have achieved the universal popularity of LOC.
Why is that, do you think?
Mostly because as the complexity of the metric itself increases, it just becomes harder to use, harder to implement consistently, and so less adopted.
People stick with what's easy.
It really speaks volumes about how hard it is to truly quantify creativity, problem solving, the actual thinking involved in software.
Yeah, absolutely. So given all this complexity and the difficulty in measuring, what does it mean for estimating how long a software project will actually take?
Ah, the million-dollar question.
Right. A common pitfall, the book says, especially on small projects, is just summing up the estimated time for all the subtasks and calling that the schedule.
Yeah, the optimistic estimate.
But that rarely works out, does it? Because it often ignores all these crucial factors.
Like what?
Well, think about all those hidden tasks. Time for meetings, endless phone calls, emails, other admin stuff.
The overhead.
Exactly. Plus all the necessary testing time, which can be significant. And then the really unpredictable part, the time to correct and retest the software when defects are found.
The bug fixing loop.
Yeah. It's like planning a road trip, but forgetting to factor in time for gas station stops, bathroom breaks, traffic jams, and, that unexpected flat tire.
That's a perfect analogy. So how do you account for these often hidden costs?
Well, the source tells us most experienced managers will actually scale a schedule's first approximation by a factor of 2 to 4.
Wow. Double to quadruple the initial estimate.
Just to build in that necessary buffer for reality.
That says a lot about how often those initial estimates are off.
It really does. And when projects inevitably fall significantly behind anyway,
Which happens.
they enter what the book calls crisis mode.
Uh-oh. Crunch time?
Pretty much, where engineers are expected to put in more time each week, long hours, weekends,
Burning the midnight oil.
just to try and hit crucial milestones, often leading to burnout, of course.
Yeah, it really shows just how much more goes into a project than just the pure coding effort. Estimation is hard.
Incredibly hard. Okay, shifting gears a bit, let's talk about the foundation. Before you even write a single line of code, you absolutely must know what the software needs to do, right?
Absolutely critical. The requirements phase.
This is the fundamental role of the Software Requirement Specification, or SRS document. It meticulously outlines functional requirements, which is simply what the system does.
Like the user can log in.
Exactly. Then non-functional requirements, how well it performs, things like speed, security, reliability,
It is.
right, and constraints, the parameters it has to operate within, like must run on this specific hardware or must use this database.
Gotcha.
And critically, the book states, if a piece of software doesn't fulfill a particular requirement listed in the SRS, it's considered neither complete nor correct. Period.
Sets the baseline for success.
Totally.
And what's really crucial here is the emphasis the book puts on the characteristics of good requirements.
Okay, what makes a requirement good?
Well, first, they must be necessary, meaning no gold plating.
Gold plating, like adding shiny features nobody asked for?
Exactly. Adding features just because someone thought they'd be cool, even if the customer didn't ask for them and they don't solve a real problem.
Right, keep it focused.
They also must be unambiguous. The book explicitly warns against using weak words like support, generally, or easy, because those can be interpreted in multiple ways.
Yeah, support can mean anything.
Precisely. Requirements also need to be implementation independent,
Meaning?
meaning they shouldn't dictate how the code is written in the requirement itself. For example, you wouldn't say a quicksort algorithm shall be used in an SRS document. That's a design decision, not a requirement.
Ah, okay. What, not how.
What, not how. Exactly. And maybe the most critical rule the book mentions. If it isn't testable, it isn't a requirement.
It has to be verifiable, measurable.
Yes, you need to be able to prove whether the software meets it or not. This really underscores how often projects suffer because their foundational requirements aren't truly clear or measurable,
That makes a ton of sense. Vague requirements lead to vague software.
or the wrong software.
The book also highlights the value of using specific SRS tags, like that example, pool SRS 00200001. What's the point of those?
Those identifiers are built right into the document, and they create what's called automatic reverse traceability.
Reverse traceability.
Yeah, it makes it really easy to link requirements back to higher-level system needs or forward to design elements and test cases. It creates a clear chain of accountability.
Okay, so you can see exactly which design part fulfills which requirement and which test proves it.
Exactly. Super useful for managing complexity and change.
Okay, so once you've solidified what to build with a good SRS, you need the architectural blueprint for how it will be built, right?
Correct. That's the software design description, or SDD document.
And the standard for that, i.e. 1016-2009, now incorporates UML.
Yes, the Unified Modeling Language. It's become the primary modeling language for software design.
UML, people might have seen those diagrams, boxes and arrows.
Probably. What's really insightful here is how UML provides a common visual language for designers. It helps everyone get on the same page.
Like a standard blueprint language for software?
Pretty much. The SDD uses things called design viewpoints that logically group different design concerns
Okay.
and then map them to specific design elements, which are often UML diagrams. It allows you to understand a complex system from various angles, structure, behavior, deployment, etc.
All right, let's maybe unpack some of those key UML diagrams the book mentions. They sound important for bringing the design to life.
Definitely.
First up, use case diagrams. What are those about?
Use case diagrams define how users or other systems called actors interact with your software. They show the main operations or functions the system provides from an external perspective.
So like user logs in, admin generates report.
Exactly. Think of it as a high-level map of what the system does for its users or external systems. Actors are often shown as stick figures, or sometimes more formally with labels.
Okay, what about class diagrams?
Class diagrams represent the static structure of the system. These are the blueprints showing the main building blocks, the classes.
Like the nouns of the system.
Yeah, kind of. They detail the data fields or attributes within each class, and the actions or methods, the operations, that each class can perform.
So the data and the behavior associated with it.
Precisely. They also show relationships between classes, like how they're connected or associated. And critically, they show visibility, public, private, protected, which controls access and supports encapsulation.
Hiding the internal details. Good design practice.
Very much so. It's like looking at the detailed blueprints of a building, showing all the rooms, what's in them, and how they connect.
Got it. And the third one you mentioned, sequence diagrams.
Sequence diagrams reveal the dynamic interactions. They illustrate how different objects or classes actually communicate with each other over time to accomplish a specific task or use case.
So less about the structure, more about the flow of messages.
Exactly. You have lifelines representing the objects involved, and messages arrows going between them, showing the communication flow step by step. The vertical position shows the order in time.
Okay, so it shows a choreography of the system for a particular scenario.
That's a great way to put it. They show the exact flow of messages and operations. The book also mentions sequence fragments, like loop for iteration, or even neg fragments.
Negative.
Yeah, which can be used to sort of comment out sequences that aren't intended for the final design, maybe for future features, or just to clarify what not to build yet.
Huh, interesting. Like leaving notes right on the blueprint.
Yeah.
And the book warns about using custom symbols in UML, right?
Yes, strongly. UML is the standard. Creating your own symbols breaks that standardization, making your diagrams potentially unreadable or confusing to anyone else who knows UML. Stick to the standard notation.
Good advice. So if we connect all this UML stuff to the bigger picture.
It provides this rich, standardized visual vocabulary. It lets diverse teams literally get on the same page to visualize, discuss, and refine the architecture before potentially writing a lot of expensive code.
Reduces ambiguity, increases clarity.
Dramatically.
Sure.
especially on larger teams.
Yeah. Okay, so you've refined your requirements in the SRS. You've crafted your design blueprint with UML in the STD. Now comes the critical step, proving the software actually works and meets those requirements.
The testing phase. Show me the proof.
Right. This is where software test documentation comes in, often following standards like IEE STD 829-2008.
Another standard.
Yep. While it defines many document types, the book focuses on the essential ones, like the software test case, or STC,
What's a step?
and the software test procedure, or STP.
How to test it. Step-by-step instructions.
Exactly.
And what's really crucial here, and often overlooked, is that testing isn't just about the final software itself. It also involves verifying and validating every document created along the way.
Testing the requirements, testing the design.
Yes. For instance, verification of the SRS ensures those requirements truly reflect what the customer needs, and critically, only what they need, avoiding that gold plating trap we talked about.
Makes sense. Check your foundation before you build on it.
Precisely. The standard also highlights something called integrity levels for software.
Integrity levels, what are those?
They essentially classify the potential severity if the software fails. It ranges from catastrophic, where failure could imply potential death or huge financial loss.
Like in medical devices or autonomous vehicles?
Exactly. All the way down to negligible, where a glitch might just be a minor annoyance, like a typo on a website.
Okay.
It really forces you to think about the real-world impact of a software bug and, consequently, how rigorous your testing needs to be. How much risk are you or your users truly willing to accept?
That's a sobering thought. It connects the technical details right back to human impact.
Absolutely.
And this connects to traceability again, doesn't it? You mentioned that before with the SRS tags.
Yes, it leads us to the crucial reverse traceability matrix, or RTM.
Okay, what does the RTM do?
Think of it as a master index or database that links everything together. Requirements to design elements to specific test cases, and test cases to the step-by-step test procedures.
Using those special tags like pool SRS 00 to 0001.
Exactly. It creates that clear, unbroken chain of accountability from requirement all the way through to proof of testing.
Wow. That sounds incredibly powerful for managing complexity.
It is. One of those powerful aspects is how it ensures that every single requirement actually has corresponding design elements and test cases. Nothing gets missed.
So you can easily see if a requirement hasn't been designed for or maybe hasn't been tested yet.
Instantly. Or if a requirement changes, you can quickly identify all the design parts and tests that might be affected. It's huge for impact analysis.
I can see that. And the book also mentions level test logs, or LTLs.
Yes, LTLs are vital too. They provide a chronological record of the actual testing being performed. They document when tests were run, by whom, what the results were.
Pass or fail.
Right. And crucially, they document any anomalies, which is just a formal word for defects or bugs found during testing.
What kind of information goes in the anomaly report?
Things like how to reproduce the bug, what the actual result was versus what was expected, the perceived severity or impact.
Yeah.
Everything needed for a developer to investigate and fix it.
So it ensures nothing slips through the cracks, and there's a clear, auditable record of the quality assurance process.
Precisely. Maintain that clear record.
Okay, SRS, SDD, UML, STC, STP, RTM, LTL, wow. That's a lot of documentation and process.
It can seem like it, yeah.
The book asks this directly. Do you really need all of this?
And the answer is, it depends.
Right. For a small personal project, maybe something you're hacking on yourself.
The book is clear. The vast majority of the documentation described is complete overkill in that scenario.
Okay, that's reassuring.
But if we connect this to the bigger picture, for most normal projects, especially professional ones, you'll probably want to have at least the STC what to test, the SRS what it should do, and the STP how to test it, maybe a simplified RTM.
So a pragmatic subset.
Yeah. However, if you're building a custom system for a customer, or especially if your software is subject to regulatory or legal restriction.
Like medical, aerospace, finance, autonomous vehicles.
Exactly. Those life-threatening environments or high-consequence systems. Then formal documentation, like that recommended by IE STD 829, essentially becomes mandatory.
You have to prove you did it right.
You have to prove it, and you need the documentation trail to back it up. So the key takeaway here is really about how you strategically balance the overhead of this rigorous documentation with the need for speed and agility, depending on the type of project you're working on.
It's a judgment call based on risk and context.
Absolutely. Context is everything.
Wow, okay. We've covered a lot of ground. We've taken this comprehensive deep dive into the engineering of software,
Hmm.
exploring its unique nature, that evolution of development models from informal hacking to agile, the elusive quest for perfect metrics.
Still searching for that one
Yeah,
metric?
right. The precision required in defining requirements with an SRS and designing with UML, and then the critical importance of testing and traceability for actually ensuring quality.
Yeah, connecting all the dots.
I think you, the listener, should now have a much more robust understanding of the systematic world that really underpins even the most seemingly simple software. It highlights that blend of disciplined engineering and still individual artistry required.
It's both science and art, really.
Definitely. So let's wrap up with a final thought. As software becomes even more integrated into, well, every aspect of our lives,
It really is everywhere now.
and we see these advanced AI tools increasingly assisting in code generation, maybe even design, what do you think will be the next evolution in software engineering?
That's the big question, isn't it?
Okay.
Will the craftsman programmer, the one with deep intuition and skill, become kind of an artifact of the past, replaced by AI? Or will their unique human skills, things like understanding subtle context, anticipating nuance, the art of truly simple and elegant design, will those skills become even more vital in guiding these powerful new computational tools?
Steering the ship, essentially.
Exactly. What's the future role of human creativity and judgment when the machines get so good at the mechanics? It's something to think about.